Hey, I'm Courtney Waterman, your tutor. Lover of anime, manga, and math. And you just tuned into another session of Tutor Me Sempai. Welcome back, everyone. Today we're jumping into a 12th grade topic, exponential limits at infinity. Now, if you're new to my channel, I'll be putting time codes in for this video in the description box below, so use it to skip ahead to whatever part of the video you think is most interesting. As always, if you have any questions about what you saw today, or even your own homework, you can always put in the comment box below, or visit my Facebook page at Tutor Me Sempai and tell me all about it there. At the end of this video, I'll be linking my 12th grade playlist, so if you're interested in that, make sure you stay tuned. This video is going to have 4 parts, so leave a like, smash subscribe, and let's get started. Similar to your trig limits at infinity, it is absolutely crucial that you can visualize what these basic exponential functions look like graphically. Now, if you recall, your basic exponential function will have a graph that's very similar to something like that. And of course, this is when your base is greater than 1. So if you have your graph here, a has to be greater than 1 in order to have a graph like this. Conversely, if you had a graph where your base was between 0 and 1, you would have a graph that looks like this instead. This is going to be your b to the x. So your a to the x is going to be where you have your base greater than 1. Your b to the x is going to have your base between 0 and 1. But these are going to be your 2 exponential functions and what they look like depending on their base. Now, we're not going to focus too much on what happens if you have a negative a to the x or a negative b to the x, because if you can visualize the positives, then you can figure out what happens when you're thrown an extra negative there. But you may start to see why it's absolutely crucial that you know what these look like, especially if you're trying to find your limits at infinity. If we're focusing on a to the x, and we want to find the limit as x goes to infinity, well, look at this graph. As you're going up this x-axis here, your function is going to be increasing and increasing and increasing. It's not approaching any particular number. So our limit for this exponential function, this basic exponential function, is going to be infinity. It doesn't approach any particular number. But conversely, let's say you're going to negative infinity now. Instead of going to positive infinity where you're increasing and increasing and increasing, notice that you are tapering off at what? At this y equals 0 line, right? So this is actually going to be approaching 0. Your function approaches 0. As you're traveling down the graph towards negative infinity, you're never going to hit it, but your function is going to approach 0. Therefore, your limit of a to the x as x goes to negative infinity is going to be 0. How about this b to the x? If we want to find the limit of b to the x as x goes to infinity, well, let's look at the graph. As x goes to infinity, what are you approaching? Anything? Yes. You're approaching 0 again. You're approaching 0 again. So our limit is going to be 0 in this case because we're going positive now. We're going to positive infinity. Conversely, if you're going to negative infinity, what's happening to your graph? Well, it's going to be growing exponentially. So your limit of b to the x as x approaches negative infinity is going to be infinity. So you see, simply by visualizing these 2 graphs, you can answer your basic exponential limit question. And of course, these are going to help when you have your more complicated limits that we'll be getting to in just a moment. But it's important to know that your graph looks like this when your base is greater than 1. If your base is between 0 and 1, this is the graph that you're going to be shooting for. Now that we've covered our basic exponential limits at infinity, let's move on to another type of exponential limit that's going to require a little bit more algebra. Let's say we're given something that looks like this. This is going to be the limit as x goes to infinity of 2 to the x plus 3 all over 3 to the x plus 1. Now it's important that you notice that the bases are different here, and you may start to panic. Don't panic. This is going to be very simple once we break down what we have to do. Now, what you want to do is ultimately get your answer, your function looking like something raised to the x power. If you can simplify this so that it looks like something raised to the x power, then we can talk about what we just looked at and we'll know what our answer is, right? Because if this is going to be greater than 1, you know that the limit of this is going to be infinity. If this is actually between, let's say this is actually between 0 and 1, you know that this is going to go to 0. So what we want to do is try to get something by simplifying this function here in the form of something to the x power. Can we do so? Well, let's try it. Remember, this is what we're shooting for. Something to the x power. We're starting with 2 to the x plus 3 over 3 to the x plus 1. I'm going to hold off on the limit just to save on space. But notice we're going to put it back. But we're trying to just simplify the function right now. So by simplifying the function, we're going to have something that looks like this. I'll throw the limit in once again at the end to actually find the limit. We're just focusing on simplifying the actual function. You can rewrite this as 2 to the x times 2 cubed, right? This is the same thing as this. You're just breaking out those exponents. Same thing for this. 3 to the x times 3. Of course, you can put the 1 there if you want, but it's not necessary. Now, we can simplify this a little bit further, right? Because this 2 cubed and this 3 to the first power, they're constants. You can kind of take them out. So you can have 2 cubed over 3 to the first power. Well, actually, what's 2 cubed? Let's just write that. That's going to be 8. 8 over 3 times 2 to the x over 3 to the x, right? You put this in front. We can do that. It's multiplication. So the 2 cubed, we evaluated that to be 8. And we took out 3 to the first out as well. We got 8 over 3. And we're left with 2 to the x over 3 to the x, right? Now we can further simplify this to be what? Well, not really simplifying, but rewriting this to be 8 over 3 times, we have our parentheses, 2 over 3 to the x power. Now we have something where it's something raised to the x power. We can throw our limit back in and see what we get. So let's put our limit back. We have our limit as x goes to infinity of 8 over 3 times 2 over 3 to the x power. You can rewrite this, of course, because it's a constant here. Throw that constant right outside as part of our limit properties times this limit 2 over 3 to the x power as x goes to infinity. And what is this? Now we already said if we have something raised to the x power, if that something is greater than 1, your limit is going to go to infinity. If that something is between 0 and 1, it's going to go to 0. Is this greater than 1? No. This is actually going to be between 0 and 1. So this limit goes to 0. So it's actually going to be 8 over 3 times 0, which equals 0. So the answer to this question here, the limit of 2 to the x plus 3 over 3 to the x plus 1 as x goes to positive infinity is going to be 0. So although this looked kind of tricky, this looked a little daunting at first, all we had to do is simplify. Simplify till we got something that was something raised to the x power. If we can get this, we can easily find our answer. Just make sure you can simplify and you follow your steps. So let's move on to our next section, which will have to simplify something that's a little bit different. It looks very similar, but it's a little bit different. Here we have another exponential function where we're trying to find its limit as x goes to infinity. However, it looks very similar to what we had before, but not quite the same. Now we have 2 to the 2x plus 1 over 3 to the x minus 1. A very small difference, but a difference. We have some coefficient attached to this x now. What do? We're going to do the same thing. Spoiler alert, we still want to somehow simplify this till we have something raised to the x power. If we can get that, once again, we can figure out our limit very easily. So let's work on simplifying this. I'm going to hold off on the limit again until the end, but let's focus on simplifying this function. Simplify, simplify, simplify. So we have 2 to the 2x plus 1. We can rewrite that to be 2 to the 2x times 2 to the first power over 3 to the x times 3 to the negative 1. And of course, you can rewrite this to be 2 squared to the x power, right? That's how you can rewrite this 2 to the 2x. You can bring out that x, raise this 2 squared to the x, it's the same thing, times 2, you don't have to write that 1 there, and this is going to be 3 to the x times 1 over 3. That's what this negative 1 in your exponent means, 1 over 3. You can evaluate that 2 squared, and that's going to be your 4 to the x power times 2 over 3 to the x power times 1 over 3. And of course, you can take your constants out and separate them. So this is going to be 2 divided by 1/3 times 4 to the x over 3 to the x. And what's 2 divided by 1/3? That's going to be 6 times 4 to the x over 3 to the x. And of course, you can rewrite this to be your 6 times, and I'm going to put that 4 over 3 in parentheses to the x power. I left the space so that we can throw our limit back in here now. We have fully simplified this to get this. Now we know that we have now our parentheses, something raised to the x power. Is this greater than 1? Is the inside, our base, greater than 1? Yes. That means this whole thing is going to go to what? Infinity. So 6 times something that's going to infinity is just going to be infinity. So the limit of this, the original, is going to be infinity. So you see, when you have something in this form where you have, it doesn't matter if it's the same base or different bases, when you have something in this form and it's just one thing on top, one thing on the bottom, your goal is to get something raised to the x power. Simplify as much as you can to get something raised to the x power, then you can easily find your limits. But what happens if you have something more in the numerator and the denominator? How do you go about doing that? Well, let's jump into our next section and figure out how. So let's say we have a function that looks like this. We have 3 to the x plus 2 to the x all over 3 to the x minus 2 to the x. And we're trying to find its limit as x goes to infinity. This looks a bit different from what we just talked about, and we have another way of tackling this one. And it may be a little similar to something that you've done before, a little reminiscent of what you had to do for your rational polynomial limits. Of course, the ones going to infinity. Remember, you found the x with the highest degree, and you divided all your terms by that. Well, we can't do that here because we don't have something with the highest degree, but we can divide by something else that's going to give us the same type of feel. And I call it the dominant term. What's your dominant term in this function? Well, let's look at it. Imagine we can plug this infinity in. 3 to the infinity is going to be something large, right? It's just going to keep growing. 2 to the infinity also keeps growing. And it's going to be the same thing in the bottom. But 2 to infinity is going to grow at a slower pace than 3 to infinity. Same thing down here. 2 to infinity is going to be growing at a slower pace than 3 to infinity. So your dominant term is really going to be this 3 to the x here because it's going to be growing much faster than your 2 to the x. Once you've identified your dominant term, divide everything by your dominant term. Then you'll get something a little bit more familiar to what you did when you had rational polynomial fractions and you're trying to find this limit as x goes to infinity. So we're going to take 3 to the x and divide everything by that. And what's 3 to the x over 3 to the x? Well, we can rewrite that to be the limit as x goes to infinity of 1 plus, and we can rewrite this now because we have 2 to the x over 3 to the x. That's just going to be 2 over 3 to the x. That's also another 1 minus the same thing, 2 over 3 to the x. And we've been doing this whole video. This as x goes to infinity is going to give you what? Well, this is going to be 1 plus, what is this going to? That's going to go to 0 because this base is less than 1, but of course greater than 0. So this is going to force this whole thing to go to 0 as x goes to infinity. Same thing on the bottom, minus 0, which means our answer is going to be 1. So once you identify your dominant term, just like you did for your rational polynomial limits as x goes to infinity, divide everything by that dominant term. And then you'll see something magical play out. So I hope you're able to follow along with today's video, and I hope you now understand how you can find your exponential limits as x goes to infinity. However, if you have any questions about what you saw today, or even your own homework, you can always put in the comment box below, or visit me on my Facebook page at Tutor Me Sempai and tell me all about it there. If you hadn't done so already, remember to leave the like. It surely helps the channel by letting YouTube know that you found the video helpful. And if you found the video helpful, so can someone else. So leave a like, hit the notification bell, smash the subscribe button, and share the video with a friend. Well, that's all the time I have for today. I'm really hoping to help with your homework. I'm looking forward to seeing you again next week. I'm Courtney, here's your playlist, and this has been another session of Tutor Me Sempai.